Okay, good morning, everybody. I hope everyone on Zoom is able to hear us. So today is the second lecture by Jed Pixley. And just wanted to make one announcement. Wherever there is this link of the announcement of this lecture series, there are links to the PDF files of these lecture notes, lecture slides, and also I think even the video recording is in the same location on the ICTS website. And those who want to meet Jed, just try to fill up that Google sheet that you might have received. Okay, Jed, you can continue.
Great. Thank you all for coming to lecture 2. So the first lecture, we talked more about dynamics from a theoretical point of view. Today, we're going to talk about several of the experimental platforms we have to ask these questions. So let me just kind of set the stage for this. So, this lecture series encompasses 5 lectures, and so this was a kind of a theoretical motivation for why you'd want to do this. And now we're going to look at all these different kind of quantum computing or quantum simulators that we have available. I obviously can't review all of them. That's well beyond the amount of time I have, but I'm going to choose 4 kind of representative cases that are important to understand. We're actually going to get into really, how these quantum platforms kind of operate, what the timescales are, what are the benefits, drawbacks, so on and so forth. I'm a theorist, so I'm not an experimentalist doing these experiments, so I obviously don't have as much knowledge as somebody in the lab in each of those platforms, but I'm going to present it from my point of view. Okay, and that'll then set us up for the lecture 3. We're going to really start getting into the physics of monitor dynamics that requires us understanding of the platforms we have to even ask these questions. Okay, that'll then, after measurements, we'll have feedback, and then the last lecture will be a tutorial on using the code base, and I'll share this information, how to download that in lecture 4, and we'll share that as well over email. So you can download the code beforehand, or probably even right before the lecture, and you could, if you want, follow along with what I'm doing in lecture 5 as a tutorial. Okay? So, what is the learning goals of today? What is the point of this talk? So I'd like you to understand the current available quantum platforms at a pretty fundamental level. And today I'm going to talk about cold atomic gases, which variants of that will take us to trapped ions and neutral Rydberg atoms, and then stepping from an atom to the qubit to a macroscopic superposition, the superconducting condensate used as a qubit is quite a bit shift, and we're going to get into that in some detail. These are several of the platforms I would have liked to have talked about. I just didn't have the time to fit it in. Okay, so I was having I had slides on NV centers and diamond, but I think it's too much information. So I welcome you to use this maybe as a springboard to learn about these others. For example, circuit QED follows directly from understanding superconducting qubits. Topological qubits are a bit different, but anyways, there was a recent announcement from Microsoft, I think a couple of days ago, in case you're following that. So it's pretty interesting. So anyways, that's really evolving, I would say. So the point of this talk is to understand these systems, how they work, what can they do, and some recent experiments that are important, okay? And that's going to then set the stage for the next lecture. So please stop me as I'm going along. The point of this for us to learn together. And I hope you find this quite interesting. So what we're going to do to begin, I'm first going to motivate why I'd want to study these quantum many-body systems. What can we do with them? What can be gained? What technological revolutionary things might happen? And then I'm going to talk about these platforms in detail. This is the core of the talk. And then I'll give you some cool experiments that have been done on these devices. And then I'll end with the ability to measure and manipulate these in real time. Okay. And I won't talk too much about those experiments because that's going to be the next lecture. Okay. So let's begin. So we all are interested in quantum many-body systems in the room and on Zoom. And what we're thinking about is a large number of interacting quantum particles. If I was actually thinking about the room, it'd be a 10 to the 23. It's obviously not going to be possible on a device or something like that. But it's going to be described by some many-body Hamiltonian. That's all these particles interacting, and it's going to be giving rise to some non-trivial many-body dynamics. Okay, and we know that interactions between particles and gases and solids already allow for several amazing and rich quantum phases of matter to emerge. For example, superfluids. So this is a gas of rubidium-87. It's ultra cold down to nanokelvin temperatures and passing through the superfluid, is the BEC transition temperature. This is absorption imaging. I'm going to get into all of this actually in detail, how this experiment's done, how this image is made. And then we also know high temperature superconductors. This is an example of a Meissner effect, levitating a superconductor above a magnet. If you ever have a chance to to see this demonstration is always pretty cool. At Rutgers, we actually have a big magnetic track. We levitate YBCO, we pour liquid nitrogen on YBCO, and you can get it to go around the track. Maybe I should have put that movie in. So the point being is this is a pretty amazing macroscopic effect of quantum mechanics. And then we also have topology. So these things are emergent, but if we could control them, it maybe represent a future of technology that we could never have anticipated. So the impact that these could have for technological advancement is, I think, hard to predict, but it's likely that it's going to be revolutionary in many regards. So, if you wanted to describe this, so these came to us. This one was predicted, but this was discovered, and so with this, we did not predict these phenomenon, right? They came to us by nature, dissolving the Hamiltonian, so to speak, letting it evolve in real time. So it'd be amazing if we could design systems to build these systems, to design the Hamiltonian that we want to solve, and just letting them run. Letting them run would just solve the Hamiltonian for you. This is actually pointed out first by Feynman. I'm actually in Feynman's lecture hall, which is quite nice. And I love this quote. And so he gave a keynote lecture. This is the first physics of computation lecture, or conference, excuse me. And I think this is his first time giving a keynote. And he gave this kind of amazing lecture where he pointed out, if you really wanted to do a quantum mechanical simulation, why would you do that on a classical computer? You should do that on a quantum computer. But the problem is nobody knows how to do that. This is a hard problem. That's what he's saying. You should be doing your calculations on a quantum computer if you want to study quantum systems. Why would you use a classical computer? It's a very amazing point. And so he's basically just saying, let's try to build a machine that realizes the Hamiltonian we want and let it run, right? That's what Feynman was saying. Okay, and now we're at a point where we're actually doing this now. And this is 45 years later, 45 years later. So what do we have now? We have a number of experimental platforms that are specifically designed to do these many-body Hamiltonians. So here's just a quick overview of an ultra-cold atomic gas and optical lattice. Here's a picture of, basically what is called connected to superconducting qubits. These are all the transmission lines. And then here's silicon-based qubits. So now instead of having a classical bit 0 or 1 to simulate it, you now have actually a quantum bit, a quantum degree of freedom, which should mimic the real quantum world. So what this allows us to do, in some cases, it allows us to access physics that we could naturally access in solid state. So for example, the liquid, the lambda transition in helium-4 was well known. This is actually data taken at the space station, just as an interesting point. So this is well beyond the discovery. But then we could do this in a laser-cooled gas. I don't think this was a surprise that you would see this, but it was revolutionary to be able to manipulate matter at this level. It led to a Nobel Prize. But there also are situations that are almost impossible to control, to study in a condensed matter system in a controlled manner. For example, like a many-body localization problem, you can never remove phonons and things like this. You can never really truly isolate a material. And so these kind of quantum platforms are ideal. Here I'm showing data of initial state of an attempt to study 2D many-body localization. I showed data in the last lecture in 1D, so I'm showing this data on 2D. And so you construct this big domain wall in 2D, and then you just ask, just like when you're pouring milk into your coffee, well, I guess in India, the milk's already added to the coffee when you get it most of the time, but you don't have to, anyways, you have to wait and long enough to see it thermalize. So if you're adding milk yourself, you get to watch and see if it thermalizes, which we all see every day. Thermalization is commonplace. But if we have large disorder, quasi-periodicity, it's possible that this doesn't relax. Okay, and so this is some signatures of putative signatures of 2D many-body localization, though it's not conclusive. This is the first experimental demonstration of that. Okay, and as I pointed out last time, correlations are not going to be sufficient to describe a lot of this phenomenon. What's going to be important is understanding the entanglement structure. And I just want to remind you what I said in the last lecture, which is that we want to think about weakly entangled states and highly entangled states. Highly entangled states are, basically representative of these many-body quantum chaotic systems we were thinking of that are highly entangled. And weakly entangled states we could think of maybe as a different phase, a different type of wave function. We also can think about critical wave functions having this logarithmic dependence on system size. Okay, so I just want to remind you of this because as we now go to these quantum systems, this entanglement is essential for these to operate in a coherent manner. If these are not entangled, the system will operate in a classical manner with no coherence. Okay, and thanks to this, there's a series of applications. For example, you can prove secure communication in quantum mechanics. You have the shortest factorization algorithm. There's recent applications in machine learning and amazing applications in quantum sensing. This has led to the private sector basically pushing to build a quantum computer on several different platforms. So IBM and Microsoft are using superconducting qubits. Sorry, IBM and Google are using superconducting qubits. Microsoft topological qubits. D-Wave is an annealer. Honeywell and IonQ are using trapped ions, but in a different manner, okay, different than each other. But the point is, there's actually tons more companies even now. This is a lot more. I'm not listing. Point being is that's beneficial for us because that competition is leading to amazing innovation experimentally. So this is going to bring me now to the core of the talk. I'm going to talk about these platforms to study and control quantum antibody systems. So what are the platforms of today? So these are kind of some of our workhorses, our cold atomic gases, trapped ions, superconducting qubits. So neutral atoms mean neutral Rydberg atoms, because the cold atomic gases are also neutral. So if you're wondering about the language there, NV centers in diamond are amazing quantum sensors. And I think we'll be seeing over the next couple of years some amazing experiments probing topological edge modes and superconductors using NV scanners. Silicon-based qubits are not nearly as evolved as these, but they also have their own advantages, and they're rather interesting. They're related to quantum dot physics and condo physics and things like this, that if you understand strongly correlated phenomenon, it's kind of your bread and butter. Okay, but as I said in the intro, that's too many platforms to talk about today. These are going to be the four I'm going to focus on, okay? So I hope we all come away with a sense of how these work, what can be measured, and what you can do with them, okay? So let's start with cold atomic gases. So we're going to start with thinking about how I build up to this point. So what atoms can we trap? So the atoms that are easiest to trap are the alkalis, though the alkali earths also have been trapped. For example, my graduate school housemate trapped in Bose-condensed strontium when I was getting my PhD, much harder than these, okay? But let's focus on these alkalis. And the reason why they're much easier to trap is because these are basically hydrogenic-like atoms. These are one electron-like atoms. So if you look at the electronic configuration, you're always landing in an S state, okay, with one electron. And so if you actually think about the energy levels, you can actually do a very good job of computing these by putting in a defect, which is basically taking into account the fact that these electrons are spread out and screen the potential from the nucleus. Okay, so it looks just like a one electron atom, but the amount of charge it sees is not the full charge from the nucleus. So you can actually get away with an effective variational wave function for the alkalis by replacing your Z coordination with effective thing that depends on distance, and you can actually do a very good job of getting the energies in these systems. Okay, it's a pretty good job of describing them. And so these are one electron-like systems, but the atomic number Z's is a function of ours, how you can think about it. Point being that these are neutral. So they're neutral, so we have to find a way to trap them. Okay? How do I trap a neutral particle? I can't use an electric field. So first, let's get the particles. Okay? So here's a conventional ultra-toldic atom setup. I'm going to go through the steps. So let's say I take sodium. That was an alkali earth. That was an alkali that I had. So I take sodium. I'm going to heat it up because it's a solid. Okay? You heat up, and out comes the gas of sodium. They come out hot, like 900 Kelvin, and so they're moving fast. And there's no way a laser could stop them. The forces from the laser would never be able to slow that atom down. Okay? So what you see here is a tapered solenoid. So what you do is you apply a magnetic field gradient. The magnetic field gradient applies a force to the atoms that can slow it down. So this is called the Zeeman slower, which is this tapered solenoid is designed specifically to stop, basically more or less stop most of the atoms when they come out. It's not going to be completely stopped, but they'll be moving slowly. So the idea is that when you start slowing them down, the atom's actually going to come out of resonance with the atomic level you're interested in. So you actually shift the magnetic field profile to keep on resonance. It's very clever, actually. And when you do that, the atoms now come out of here, and they're moving pretty slow. So slow that you can now apply 6 laser beams, counter-propagating laser beams, to trap the atoms. This is called optical molasses. Okay? The idea is that you use a scattering force, the scattering force from the photon momentum getting imparted out of the atom, and a scattering rate from opposite force. So let's just do a 1D example. So if you do this in 1D, you shift them off resonance, and this scattering effect, this is the photons emitted after it's excited, it's going to produce a force, scattering force, which when you stare at this a little bit, you're going to, hold on, let me just tell you these parameters. So this produces a scattering force, which depends on the laser intensity, how far I am from resonance, and the spontaneous decay rate of my excited level. Okay, so this is rather fundamental. You can compute all these, and then you can show that this is actually a restoring force. So if the atom wants to go to the right, it comes back to the left. If it goes to the left, it comes back to the right. If you do this on all 6 directions, you're going to hold it together in one spot. This is what we call optical molasses. Optical molasses is not enough control. In reality, what people actually use is they actually add a magnetic field. This is a magneto-optical trap, so they also add these coils so that they can have an additional degree of freedom from that magnetic field. This just increases the number of atoms you trap, because you want to have a large condensate, a large density of atoms you can work with. If you end up with trapping too few atoms, you can't do much science, right? It's a neutral atom. So the magnetic field is, again, by the scattering. So the scattering is a thank you. So it's different polarization. So you look at the difference between right-handed and left-handed polarization, and that's imparting a scattering force as well. Thank you. Absolutely. Very good. So once you do that, you can just keep cooling it down by the scattering force, but there's a fundamental limit to how cold it can be. This is known as the Doppler cooling limit. Okay, so the theoretical limit that you could get for sodium was 240 microkelvin. But when people did this experiment in reality, it went 2 orders of magnitude smaller. Okay, this was an example of nature working much better than you ever would have thought it would, and it's because of another mechanism actually taking place, which is known as cis-fis cooling. I'm not going to get into that, but the point is that these neutral atoms actually get much colder than we thought by this process, which is fantastic news. But it's still not degenerate, okay, because these are very dilute. So now we have these atoms. They're very, very slow. We have them in this magneto-optical trap. We want to let go of that and put it into something very stable. It's going to sit there. This is now goes under. We're going to confine them with a magnetic trap. Okay. So if you think about a radial confining trap from a magnetic field, these are currents producing this kind of magnetic field pattern. It produces a potential that's harmonic potential in 2D. You can then add a third axial confinement, and that produces a harmonic potential. So the atoms want to sit down here, but the hot ones are going to sit up here. The hot ones have high energy. They're going to sit at the top. Okay. Now what we want to do is we want to get these systems even colder. This is known as evaporative cooling. So we have our atoms trapped in our potential. As I said, the hot ones are near the top. They have the high energy. So you just start lowering the top of the trap in an adiabatic fashion. When you do that, the hottest atoms leave, the lower atoms equilibrate, and there's actually no lower limit to this process, and temperatures have been reached well below 10 nanokelvin. Okay. So this is how you get your ultra-cold atomic gas, and now you want to make it correlated. To make it correlated, you need to make the atoms feel each other strongly, and what you're going to do is you're going to turn on an optical lattice so that they can sit on top of each other, they can really repel. You do this with an electric dipole force. So this electric dipole force is related here. It's basically the gradient of this interaction. And so if you produce an electric field standing wave, it's going to produce a dipole potential, which is co-squared, and it's going to hold the atoms in this potential. So now I can place, this is going to be on that harmonic trap, and so the atoms now can sit in these minima, and then they can feel each other strongly from the scattering length. Yes? Fantastic question. So you would look at the distribution of density, and if it's high temperature, it would be Maxwellian, and you could see the distribution of the velocities and infer a temperature. But if you go through Bose-Einstein condensation, it would be driven by the Bose-Einstein distribution, and you'd have to. So basically they fit the profile of the clouds to extract the temperature. They don't have a thermometer, right? So it's all based on statistics. There can be, absolutely, though you want to minimize that, because what that does is it excites other atoms and then they get kicked out of the trap. So you try to minimize anything like that. And when I get to measuring these things mid-circuit, like in the middle of the dynamics, that's a huge problem. But if you want to measure it at the end destructively, it's okay. The idea is you want to trap it and then you let it go. So I'm about to do that right now. So you want to make measurements. Okay. So now what you're going to do is you're going to let the trap go. Okay. And when you let the atoms fall, you can then shine another laser beam, and when the atoms get absorbing a photon, it'll pick up on the CCD camera as a dark. If the photon just goes past, it'll be bright. So that shadow is the density profile. Okay. And this is exactly what I was showing you in the introduction. This is the density profile. So this is how they infer the temperature from that Maxwellian gas. Yes? So go ahead, sorry, this one? Yeah. This is on the harmonic trap. So you think the harmonic trap has this optical lattice potential, and down near the minimum, it's pretty flat. Though there are advances where they call them box traps, where you can make it much harder walls, but you have to work harder. So that technology is not as standard. But in principle, you could remove these kind of spurious, weak wall effects. Yeah, great, thank you. Please keep asking me questions. If I reach something I don't understand, I will just tell you because I'm not doing the experiments. But I've been quite involved in some of them. So as I was just saying, so you can infer, this is like Maxwellian, right? So you can infer from that Gaussian, and then you clearly have this amazing Bose-Einstein kind of density profile. So you have to compute theoretically a density profile, and you can then fit that and extract velocities. You can also do something much more amazing these days, which is single site imaging. So this is like a 2D optical lattice, and based on how they refocus all the lasers, they can actually get single site addressing. So you can, here's several images of single site measurements of the atoms. Okay. So this is known as a quantum gas microscope and single site imaging. So what can we do with some of these? I want to just kind of set the stage for some experiments from this before we go into the next systems, because it's already pretty interesting. So these cold atomic gases are really ideal analog quantum simulators. You can really engineer Hamiltonians. They're ideal to let systems evolve. Once you've engineered them, you can also control the interactions via Feshbach resonance, which I haven't talked about, but it's a way to control the scattering length in certain atoms that have one. And we can also do Floquet dynamics because we can apply lasers periodically. So it's very natural we could do the Floquet models I talked about last time. I'm going to show you that right now. So the first thing would be you could do, one of the first things I was saying here is watching simple states relax or not relax. Here's an example of Anderson localization due to speckle pattern disorder. So here's a delocalized phase, and the disorder is really strong. You can see it's very localized. Okay. As I promised, so last time we spent a lot of time on these kicked top, kicked rotor. Okay. Here's my quantum kicked rotor. You can realize that in this system by applying your potential. This is your optical lattice. You apply that for some time. Then you just let it evolve. Potential, let it evolve. So you're doing exactly the kicked rotor. Okay? And here's this is the first experiment was in 1995, and they observed the dynamical localization that we derived last lecture. Okay, so this was directly observed on a gas of sodium atoms through time of flight imaging. We're just measuring this momentum profile. You can see it right here, localized. So here's the observation of dynamic localization. Oh, please.
Well, how do they?
So they apply the potential. So they apply the optical lattice potential, basically, for some time. Periodically. You apply it, and then you turn it off, and you let the system evolve. Let me go back. So you apply it for some time t, which I should have had up there. Then you let it evolve. When it evolves, it just goes p squared over 2m. And then you hit it again, let it evolve, hit it again. It reached period. It's really, yeah, it's pretty cool. And then you realize directly the dynamic localization as we predicted. Now let's go to the kick top. Okay? Kick top we can get by trapping a single cesium atom. I didn't tell you really about cesium. Turns out cesium is another atom you can trap with a huge magnetic moment. So these actually have rather large dipole-dipole interactions. So if you thought about a Bose gas of cesium, you actually have to deal with the fact that you have non-trivial magnetic interactions that affect the superfluid. But let's not worry about that. Let's just take one cesium atom. We've got a big magnetic moment. So now that J that I had in my last lecture is now my hyperfine F. Okay? And now I can do the kicked top model by applying a short magnetic field post to rotate F about Y. That's the first one. And then you have to do something a bit more non-trivial where you do like a combination of rotations that depend on the spin state. That does the square. Okay? And you do this periodically. If you remember, this should be chaotic. And so if you look at Husimi distributions, the experimental data and the theory really match incredibly well. And the demonstration that they had of some chaos is they took initial states from these attractive islands, from these integrable islands, and you don't see it relax, and you take it from the chaotic region, it relaxes. Okay, I'll show some future data from superconducting qubits later on the kick top as well. They can measure the entanglement of this qubit. But this is this is following up our lecture 1 where we had the theory for this. Now I'm showing you some experimental data directly on that model. Okay, so cold atoms are amazing, and now they're going to set us up for trapped ions and the neutrals. So now let's get to trapped ions. So first, let's just think about magnetic forces and electric forces. So everything I was doing for the neutral atoms was using these magnetic field gradients. So the kind of force I was imparting on a single atom was very small relative to the electric force I could impart on the same scales. So basically, if you have an ion, you can impart forces 10 to the eighth greater than the neutral atoms. What this means is that you can make the trap incredibly deep relative to the neutral atoms. This is very important because these trapped ions are going to be created by ionizing a neutral atom. So we're going to hit it pretty hard, and if we didn't have this big electric trap, it would just shoot away, okay? So let's think about how this is done. So we have the same kind of setup, but now we have to add an electron beam to ionize the atoms, and they're going to kick off the outer electron of some fraction of the atoms. And then once those are charged, we can trap them with electric fields. The ones that are neutral, we don't even care about. And the ions that have been trapped, I list here, and that's because they have a particular atomic shell structure that once ionized, they are easy to control, okay? This makes the cooling process easier, though this is not like fundamentally limited by this, okay? And now these ions have a really large recoil energy because we kick them with this ionization beam. So they're going to basically come out really hot. But this depth of this trap is so deep, it's okay. We can actually still trap them. This is actually a pretty non-trivial point of the ion trap. And if you want to now cool them, you can actually, this is all done in a vacuum, but what they do is they put in a little bit of helium gas, which scatters off of the hotter atoms and thermalizes and cools them down. And then you can also Doppler cool them, the same scattering force I mentioned the last time. So what you get then is something that's very stable once you can hold them in place. The problem is with an electrostatic field, you probably already know this, you can't hold a charge in place. It's an Earnshaw's theorem. The charged particle acted by electrostatic forces will not remain at rest. So I think this is Dave Wineland who won the Nobel Prize for this. He realized that let's think about a mechanical analog. So if you take this saddle, and you've maybe seen these movies in classical mechanics, and you rotate the saddle fast enough, the ball stays in the middle of the saddle, right? So you just have to rotate this appropriately. So now let's do this with electric fields. So we're going to place our ions between two positive charges, so they don't want to go out, and then we use AC electric fields to produce this rotating potential, okay? This is called the Paul trap. And indeed, once you do that, you can hold the ion at the middle of the bottom of the trap. So this is an image, for example, of one example of 8 or 10 ions. Okay, and then if you want to know what do I need to do to make these stable? These ions, they're vibrating, right? They're moving around because they're not totally stationary. They can't be stationary, as I just showed you. So what you need is you can solve this equation of motion, and you need that this oscillation not be too great. Okay, so you can show that for these ions to remain trapped, this parameter Q can't be too big. It's just a so you tune your parameters such that this is always satisfied. That's a way to know that if these ions are going to remain trapped once you've done all this. One thing that's rather amazing about trapped ions is actually that in the cooling process, for example, for barium, the photons that are emitted are actually at visible light. So you can see the ion visibly once you've trapped it. It's absolutely amazing. And here's an example of some of that data. And this is because it's electric fields. This is stable for a long time, hours, days, even weeks. They've been holding atoms before. Okay, so these things are really impressive in that regard. And what can we do with them? So we can do many body physics. So here's 60 atoms trapped. You can see right there. And here's a 2D lattice that you can also make. It's slightly different than what I just described. That Paul trap I described as 1D, but there's more ingenuity. You can make a 2D trap. These systems, basically, these ions are spin moments, and they interact with long-range interactions due to the phonons in the ion chain. So these ion chains have a bunch of phonon modes, and they then couple these ions together through a long-range interaction, which is controllable. So you can't see this too well, but this alpha can be tuned. This is alpha going between 0 and 3. So really, it's really, I think, highly accurate between 1 and 3, because it's getting a little bit tricky down there because the detuning is too small. But they can very controllably control alpha. Okay, that's the idea. So this is them controlling the couplings by varying different parts of the experiment. So they can realize this kind of a model. They can realize transverse Ising models of long range. They can realize spin 1 models. Here's an example of some beautiful data from Chris Monroe's group, which they chose different long range interactions, and they applied a local quench, and they watched the magnetization grow after a local quench. So this is some of the many body physics you could do with trapped ions. But distinct from the cold atoms, people realized early on, this is a seminal paper by Ignacio Serac and Peter Zoller, which basically showed that you could do quantum computing with trapped ions. They realized this in 1995. It's a seminal piece of work. So what they realized is that universal quantum computation is accessible via optical pulses on these ions, which can do 1 and 2 qubit gates. So for example, a 1 qubit gate directly accessible, you can transition between ground state and excited state, then the 1 qubit gate. 2 qubit gates are also possible under this particular form. And with these, you could do all universal quantum computation. These are known as the Mormor-Sorensen 2 qubit gates.
Sorry, Jed, can I ask a delayed question? So in the previous slide, if it is phonon mediated, why is there a reason why it is restricted only to up to 3, like 0 to 3?
Well, I think that's just, I think that's probably they're detuning, you can't, it's limited by the detuning. They're detuning from the level. There's a lot of
So I mean,
experimental
in
consequences.
principle, it is possible to go beyond 3.
No, I don't think you can't detune that far. You're so far from resonance, it doesn't mean anything.
I see. So
It's related to how far you are from the resonant level. If you go beyond 3, you're just like, there's nothing. You can't even get to 3, really. It's probably really around here.
I see. Okay.
Yeah. Because the detuning has gone so far away, you're losing your control.
But you can go all the way up to 0.
Yeah, roughly, I would, when you talk to them, they say we can go between 1 and 3.
Okay.
So I'm not a trapped ion experimentalist, so, I trust what they tell me.
Thanks.
I think they're a little bit, I think I don't know how accurate it is between 1 and 0. Maybe somebody online could comment. I don't know.
Thanks.
Yeah. That's alpha, yeah. Alpha they can tune roughly between 1 and 3. And I can't really see it that well here, but this is the spin decay, and this is the different alphas that they can reasonably reach. I think the alphas they can get I guess they can get to 0, but I don't know. They don't really show that all to all very much. That's a good question. I don't know. I'm not sure. No. Okay, fantastic. So we have our 2 qubit gates. So let me summarize what has been. This is kind of the state of the field now. This is not like best numbers. This is like a rough estimate based on the literature. So the gate speeds of these are optical pulses. So these are slow. These are microseconds. But the fidelities are very high. And look at the coherence times. Hundreds of seconds, over a minute. Okay, these are very long-lived systems. Okay, so these coherence times are really remarkable despite the slow gate speeds. So let's take that away for the ions. The ions have slow gate speeds, really good coherence times, and good fidelities. Now let's go to neutral atoms. Okay, any questions before we go to neutrals? So neutral atoms, when we say neutral atoms, we really mean, oh, please, yes. Fantastic question. So, okay, let me go back. So ion Q worked on these chains. The chains are not scalable because these edges have huge amounts of oscillations and phonons. The stability is really in the middle. So a chain is not going to scale. Quantinium designed the entire system based on a so-called shuttling procedure where you can bring in another qubit without it making the other qubits more noisy. So the quantinium procedure is substantially more difficult, but in principle should scale. So yeah, but I think everybody's kind of going towards the shuttling procedure. So yeah, fantastic question. So quantinium I think has over 100 working qubits right now, for example, and it's just growing. They do need correction. They're going to need error correction. They're not doing it yet, really. So they're able to do a lot of experiments without having to do the error correction directly, though that's where everybody's moving to. Yeah, great question. Thank you. Okay, so neutrals, good. So neutral atoms, kind of this, I think this came as a surprise, I think. Maybe, I don't know, maybe not to everybody, but the ability that these can do is really remarkable. So let's start describing these. So when we say neutral atoms, everybody says the neutral atoms, they really mean neutral Rydberg atoms, okay? Or Rydberg dress, because all the atoms are neutral, okay? So what we really mean is, so what are Rydberg atoms? I imagine maybe you encountered Rydberg atoms, maybe in a quantum mechanics class. There's just basically hydrogenic solutions with a huge atomic number. So that your radius, right, scales like the square of that number is big. If you take something like that, that's a micron-sized atom, okay? So if you want to think about what that's going to do, if you apply electric field, it's going to produce a massive dipole moment. So massive that if two new Rydberg atoms are going to interact off resonance, they're going to interact with a van der Waals interaction, and this overall prefactor is scaling like n to the 11, producing a very large interaction, okay? So Now what I want to do is I want to take my atoms, I put in my 1D optical lattice, as I just described to you, okay? And now I'm going to apply another laser tuned to a Rabi frequency to that Rydberg level, to a low-lying Rydberg level. What, question? So they're going to be optical tweezers. They will be. But for right now, let me just put them in a lattice. This is before the tweezers. But yeah, absolutely. That's where I'm going. And I just want to keep it simple. Okay, so we put it in the lattice and we can start dressing them. And when you dress them, after you apply a rotating wave approximation, because they're not tunneling to each other, you can either, down is ground, up is Rydberg. So you can go between ground and Rydberg via this Rabi frequency. This is detuning, and this is the interaction I just told you about, okay, on the lattice. So now if you go to this limit where V1 dominates over all the other scales, what you see, this is a Rydberg blockade. So if I have one atom in its ground state, and if I excite this one atom to the excited state, my neighboring atoms feel a very large potential, so that I cannot excite my neighboring atoms. Okay? And this is a constraint, and we saw this under the name of PXP last time. So this model can be derived. So if we constrain the Hilbert space into this blockade region, meaning that nk plus 1 always has to be 0, if we form our projector under the ground state, we can realize that, what this sigma x does is it flips the spin at site k. So you can only flip that if its neighbors are also down, right? Because the neighbor's up, it gets blockaded, okay? So what that means is that this flip between ground to Rydberg has to have this projector, meaning my neighbors have to be in their ground state. So when you do that, you arrive at this Hamiltonian, which is precisely the PXP model we talked about last time, which on resonance, you can set that term to 0. So this is now this experiment I talked about last time. This is now optical tweezers, as you were just saying, and this is seeing these scar states in the relaxation. I presented this in lecture 1. This has now been extended way beyond that, 2D, 1D, much bigger chains, up to 200 atoms, and verified in great detail, okay? And so the revolution, though, that came here, which I haven't told you about, is these optical tweezer arrays, which was already pointed out. Thank you for that. The idea is actually that these individual atoms can be trapped in tunable, basically two-dimensional arrays of optical microtraps. So these are optical tweezers, and you can shuttle in each neutral atom as you want, and you can make any basically lattice arrangement you desire, okay? It's truly remarkable. And so, because when you bring them together, they would never feel each other if they're in the ground state, but by using that Rydberg level in the blockade, you can get them to strongly interact with each other, okay? So this is the first demonstration of using this kind of array of atoms to bring together. So they made like a chain, they made 2D, they made a ring, they made a 2D lattice, okay? This opened up an amazing amount of flexibility and control over atomic physics. Oh my God, you can't see that at all, sorry, okay. That image is very pretty, but they can make 1D, 2D, 3D geometries. These should be 3D pictures. Here's a knot they made in 3D. It's really remarkable. So you can make quasi-crystals, you can study quasi-crystal magnetism. A lot of interesting questions we can now address with these systems. And this kind of, these analog quantum antibody simulations of quantum magnetism opened up totally new directions. So here's one example with 256 atoms. What they did is they slowly ramped through the 2+1D Ising quantum phase transition. So they realized the transition with Ising model in 2D. And this is their setup. And as they ramp through it, they can see critical phenomenon that agrees reasonably well with the prediction of this 2+1D quantum Ising transition. So this is a demonstration of viewing quantum criticality on this device. Ignacio and Peter also realized you could do quantum computing with these guys. So these are two seminal papers involving Misha Lukin as well, as you can see, and Steve Ralston. And so what they realized is that these also can be used for quantum computing, but in a different way, in a much different way than the ions. So quantum computing with neutral atoms is basically, now again, you're going to address either two of them at a time or one at a time, and then you can make like a circuit diagram. This is like basically a circuit diagram of different gates, and now a 2-qubit gate is going to be you act on these two atoms and you bring them together, they feel each other from the Rydberg interaction. So any 1-qubit gate is accessible through this process, but the 2-qubit gates, you really can realize a C0 by doing a CZ gate combined with Hadamard. And so this is the native gate in this system. I'm not going to get too much into that detail, but these are some details about what they can do easily. And these systems also have optical addressing, so we are slower gate speeds, but very high coherence times. And the thing I have a T2 star here because these actually, this excited level in the Rydberg level does have a bit of loss, which is why this is a Ramsey coherence time. And these fidelities are also quite good. So again, this is rather similar to the ions, where they don't stay as long. This is an example of running one of these continuously for 2 hours. It's pretty impressive. But it's unclear exactly how long those can be stored, but these are quite a long time. Okay. So with that, any questions before we go from atoms? Yes, please. Yes.
So which one is good in the platform or they are exactly
For the surface code?
you have the
Yes.
stuff here.
Absolutely.
What is it?
For trapped ions or the Rydbergs? Okay, so that's a fantastic question, and it kind of gets to a little bit of the talk. So the mid-circuit measurements that you need to do the error correction, my understanding is that the ions are now getting to the point they can do that, and that neutrals are a bit easier to do the mid-circuit measurements. So I'll get into why that is, because when you want to measure an atom, it's going to fluoresce, and if it hits the nearby atoms, it can kick them out. So you have to shelve it in like a state that's dark to the other atoms. And for the Rydbergs, it turned out to be a bit easier, but there's a paper I'll point out from a year ago for the ions that can do it. So I don't know. Yeah, I think it's a matter of like the technology getting there, but it seems that both of them will be able to do it. But the demonstration of the surface code so far has been Google's, and I'll mention that at the end with five. It's been the superconducting qubits still. So let's get into these. Yeah, thank you. Does that answer your question? Yeah, good. So we're going to shift gears quite a bit. So before I do that, let me just acknowledge the 2025 Nobel Prize in Physics, which was for the discovery of this transmon qubit. And here's the PRL that discovered it. So if you ever, you should always feel good about publishing a PRL. It's, they win Nobel Prizes, okay? So don't worry if it's not a Nature paper or something. So now I want to move conceptually, though, from the atom is the qubit, which is how we've been thinking this whole time, to using a macroscopic quantum state as my qubit, okay? Which requires me to do a little bit more background to even talk about how this works, okay? So let me do a little bit of background on superconductivity. I imagine you all have seen superconductivity at some level, but I'm going to do some background, the background I need to get to the point to talk about this qubit, okay? So these are all conventional superconductors that are used. I should say, though, that there are proposals to use BISCO, based on some of my work, and to make qubits out of BISCO, twisted BISCO, which is a pretty interesting direction, but that's totally way off. So what's actually being done is conventional superconductors you understand quite well. Aluminum is really the workhorse, though there's demonstrations that niobium also works very well. And the idea is when you have a conventional superconductor, the attractive interaction between the electrons is all phonon mediated. Okay, so your BCS Hamiltonian, you simplify by taking the phonon interactions about the Fermi surface, within the Debye frequency of the Fermi surface to be attractive. Okay, and then you get a superconducting order parameter that has a magnitude and a phase. It's complex, and it'll be gauge dependent. So you can solve for this at the mean field level. Okay, and you get a gapped in the S wave for these conventional superconductors. You get gapped excitations of the superconductor, which allows you to solve for this superconducting order parameter. At t equal to 0, you can derive this is the coupling of the density of states of the Fermi energy. I imagine everybody's seen this. I want doing all this to be able to write down my mean field wave function, my BCS wave function. Okay. So once I have my BCS wave function, I can start moving towards trying to get to how I can understand how I can even make a qubit out of this thing. So my BCS wave function is actually a bit non-trivial because it's going to depend on a gauge. And so if I, for example, ignore the normalization for the time being, I can rewrite this as a coherent state where lambda dagger creates Cooper pairs. So I have it's basically a series of Cooper pairs being created. I can now apply gauge transformation to my underlying fermions. My gap, as I said, is not gauge independent, it's gauge dependent, assuming an order parameter. And as a result, my BCS wave function will also depend on that gauge. If I now act with the number operator on my wave function, I pull out a factor, and you can see that this number operator acted like a derivative on the phase, which tells you that n and phi are canonically conjugate variables. So phi is like my position, and n is like my momentum. Okay, I imagine we've seen a lot of this stuff, but this is where we can launch now into thinking about a Josephson junction. So Josephson tunneling is if you have two superconductors separated by an insulating barrier. You want two identical superconductors, so it's like aluminum, aluminum, aluminum oxide. And I thank my close colleague Vatsan Chakram for his really nice lecture notes. Any mistakes are his lecture notes? I'm just joking. They're very nice lecture notes. And so the point being is that you have a phase difference, and that phase difference is going to drive basically a current through this. So if you apply a voltage, your Cooper pairs are going to tunnel from left to right, okay, through the insulating barrier. And you can think about this process actually in some sense as a tight binding model where you're tunneling, you're hopping Cooper pairs from left to right, okay? And so you get tunneling Hamiltonian with Josephson coupling energy. I'm not deriving this, I'm inferring it for you, but this is all based on the normal state. If you just solve this tight binding model, as we all have done several times in our life, you have plane wave solutions, okay? And you can then rewrite this in a very clever manner in an operator form. So you can see that this tunneling Hamiltonian looks like cosine of the phase. Okay, so now if I look at this a little bit more, I can derive exactly what I wanted, which I think about the basically equation of motion for the number of Cooper pairs tunneling. It's going to be related to the sign of the phase difference. This is phi 1 minus phi 2. I should have written that down. M is the number of Cooper pairs hopping. So you should think of that. So M is, I have NL Cooper pairs. I remove one and I add one. So it's a little non-trivial. It's not, yeah, exactly. It's not just the hop. It's really the tunneling of Cooper pairs. And this is kind of like an easy way to do these derivations. If you want to do it more rigorously, you have to work a bit harder. But for the sake of, I think, the presentation, this is a really nice discussion from Steve Gerben's Lezouche lecture notes, which I recommend that you take a look if you're interested. Okay, so here's our tunneling Hamiltonian written as a cosine of the phase operator. And then you can see that you can get the equation of motion for the number of Cooper pairs tunneled, which is related to sine of the phase difference. And indeed, we obtain the current. This is the famous Josephson relation between the current and the phase difference of the superconductor tunneling. And this is limited by the critical current. So you apply voltage that's too high, you're going to kill the superconductivity. If the current is too big, that's the critical current value. If you apply less than that, you have superfluid. You have super current flow. Okay, so now I want to put this Josephson junction as a circuit element into a system. So this is the circuit element of the Josephson junction. You probably didn't see this in undergrad, but you should maybe see it at some point, which is this X. Okay, you can upload that to a capacitor and to ground. The capacitor has a charging energy. We put some offset charging energy here. Okay, and this goes like Q squared, as we all know, capacitors have that energy with a particular charging energy. And now my Hamiltonian, written as operators, is here, and I can write it in the charge basis. Okay, and I can try to do some kind of perturbation theory to get a feeling of what's going on. So if I take EJ to be very small, I can treat this perturbatively, and as Vatsan explains very nicely in his notes, you gap these excitations. So this is the offset charge, but you can think about 0 to 1 here. So if we zoom in from 0 to 1, this is the 0 level. The 1 level, I now have a gap. So you can think about this as the ground state, this is the excited state. And so, if I want to transfer 0 to 1, I have to do like a flip, okay? So if we truncate to this lowest level, and forget about these higher excited states, if we're low enough temperature, we can truncate, and we arrive at a spin qubit Hamiltonian. So I just showed you how this actually ends up as a qubit with a spectrum that can now be, single qubit rotations can be driven by just driving the system at this frequency to go from ground to excited. Okay, so I've finally got a qubit, worked very hard, and the summary basically is this transmon is probably the simplest superconducting qubit. The key element is your Josephson junction. It's nonlinear because of the cosine. And that nonlinearity is essential because if I had a harmonic oscillator, these equally spaced levels, I could not address ground to excited state individually. But this anharmicity between basically makes it so that ground to excited is a different level than the rest. So you can address this directly with microwave pulses. Is essential. Okay? And this forms this is called the transbond qubit. So there's tons of different types of qubits. It's well beyond my expertise. We have charged qubits. This is what I've told you about. I just told you about the simple Cooper pair box, but they can get more and more sophisticated. The idea is your qubit is actually a superposition of the two charge states 0, 1 on the island. The other approach is you inductively shunt the Cooper pair box, and this is a progression now to the fluxonium qubit. And here the superposition is through persistent currents in this loop of the inductor. Okay, and so these are the two different kinds of qubits. There's a lot of different types you can take. Here's the so-called periodic table of qubits, of superconducting qubits. These are the non-inductively shunted ones, and here now the inductively shunted. And you can, based on where you are, you have different levels of sensitivity to different types of noise. So, you know, depending on your application and what you're trying to do, you might be using a different one. There's been a massive effort from IBM and Google to scale these up. This is IBM's Heron quantum computer with 156 qubits. Here's Google's Willow with 105, for example. So they've been putting a huge amount of effort into scaling up these superconducting qubit devices. And just to give you a sense, so now our gate speeds are fast. These are now nanosecond gate speeds. These are incredibly fast relative to what I was telling you about before, though the measurements are not nearly as fast. I have to double check that, so take that with a grain of salt. And these coherence times are now much less. So much faster, but less coherence. So to summarize what we've learned, so in terms of quantum computing, the trapped ions and neutral atoms have these long coherence times, but are controlled via optical pulses. So the gate speeds are innately slow. Superconducting qubits are incredibly fast, but they have less coherence. And so it's unclear who's going to win the race to the quantum computer. So who will win, I don't know. But if you ever got to work with some of these devices, I mean, these superconducting qubits are so fast, there's so much data coming out that classical communication can actually become the challenge, not even the quantum, just interacting with all the data in a fast enough manner. So it's pretty impressive. Okay, so any questions on the, yes, please.
One question. So the tunability of this two-level system.
Yes, of the superconducting qubit.
Of the superconducting, there you can tune it, right?
Absolutely, with microwave pulses, yes,
exactly.
or a voltage driving the gate voltage, for example.
Right. But the other examples given,
those are optical pulses.
Right.
All the atoms are interacting with optical pulses, so the speeds are substantially slower compared to microwave pulses.
No, but in terms of
maybe that's what your question is.
In terms of like tuning the Hamiltonian.
You can do both 1 qubit gates, 2 qubit gates are possible with all of them. It's just these numbers are giving you a sense of the merit. So they can all do universal quantum computation. It's just like which one is less noisy, which one has more fidelity, which one is faster, slower. You know, it's a trade-off, and it's unclear, how it's going to go. I mean, as we've been seeing over the last 10 years, amazing progress. So, okay, great, thank you. Yes. Yes. So that's actually circuit QED. So that's a whole platform. Yes. Yes. So if you use the cavity mode, you can get an order of magnitude longer coherence. But the thing is, you always end up having to interact with them through a transmon. So actually, Watson, my colleague Watson, that's what his lab is doing. That's what he's building up a multi-mode circuit QED. And the idea is actually these might be more like a quantum memory, not a quantum processor. It's more like you could, you have an order of magnitude longer coherence, so you could put the memory into those cavity modes, and then when you want to fetch it a little bit later from your processor, that's kind of how they're thinking of doing that. But you could do quantum computations directly with those cavity photons as well. But you'll end up, getting bit some level by interacting with the transmon a little bit. But so yeah, very nice question. So I didn't have enough time to get into that stuff, but that's really rich and it's a really interesting direction. And the notion of a quantum memory, if you want to build a quantum computer, everything I've really talked about is really just a processor, right? Everything I've talked about is just a processor of the stack. It's not the whole stack of the quantum computer. You'd actually need memory, you need a lot of other things, right? So you can think about those optical cavity modes as maybe being our memory. Yeah, fantastic. All right, so let's now talk about, before we leave the era of unitarity, let's talk about experiments using some of these on unitary dynamics. Some more examples than I've given already, okay? And I want to kind of tie these to lecture 1, okay? So we talked about ETH. So let's think about a test of ETH. This is I have to say, this is a really, I mean, I saw this data, it was really impressive. I was a postdoc at the time, and it blew me away. So this is a direct measurement of entanglement. It's a small system, okay? But it's a direct measurement of entanglement on an ultra-cold gas. And what they do is they measure the second Renyi entropy by taking 2 identical copies of the system and then letting them interfere. So you take rho and you let them interfere and you trace. So you basically get trace squared. It's really amazing. And they actually were able to measure the second Renyi entropy. Oh, this just died. Sorry. Is it going to switch slides? Okay, interesting. So you can see that now, this is basically purely thermal, and after a quench, they're basically getting thermal relative to a ground state. So they're really seeing a thermalization and becoming largely entangled. Okay. There's also an experiment on the quantum kick top, though I already mentioned this before, but it was able to be done here is they could basically, I don't have the laser pointer anymore. Do I have a physical pointer? Basically, what they're able to do here is they can measure the entanglement of that 1 qubit by doing a huge amount of measurements, tomography on that 1 qubit. Okay, so they have 1 qubit, and then they interact with it a bunch of times in kicking it, and they can realize this kicked rotor model. So here's just some of the actual entanglement entropy that comes out. So K.5 is the lecture I told you is integrable. It does not thermalize. And K is 2.5. It is chaotic, and it totally thermalizes the entanglement. Oh, please. Single qubit. They think the qubit with everybody else, with the environment, with the kick. Yes, thank you. With the kick. Exactly. So it's kind of like if it's integrable, it just follows its orbits. Is the intuition that they had in the paper. But once it's chaotic, it should explore all of phase space. And that their way they're probing that was entanglement. They didn't probably have to use entanglement, but they wanted to lop to your paper, is my guess. Considering it was already measured, in other systems. So I don't know.
Just one part is big.
I agree. Yeah, I'm with you. It's just coherence. I think you just think of the coherence. This is just the coherence, right? It's just the coherence. Absolutely.
What is being measured?
Yeah. Sorry. So they basically realize the kick top using superconducting qubits, and they think of like one of the qubits, as the top, and then they watch it go around a bunch, or they that's going to be a spin half, and they can make it bigger and bigger and bigger, and they can make a bigger spin, and they call that one spin. So they vary this J. They vary this J. So that one spin might be a bigger collection of spin halves, but it still wouldn't be entangled. It'd still be coherent. With you 100%. Okay. Yeah. So this is, I think I'm just trying to show you that you can do these analog simulations using all these devices. A lot of these models we talked about as like workhorses to understand quantum chaos, they're actually really experimentally realistic systems. We're not, we're theorists, but we should never go away from the experiment, right? We should always be tied to reality. Okay. So here's using trapped ions. As I told you, you have these kind of long-range interacting models. So what they did is this model, this is like the transverse Ising model plus long-range interactions. So that transverse Ising model is integrable. The long-range interactions are going to thermalize you. But if you can make those long-range interactions weak enough, that thermalization is very slow. And so what they did here is they put a single spin excitation and they watch it grow very slowly. This is the end of the spin evolution relative to fully polarized. Oh. Thank you. Oh. Doesn't like that. The keyword cannot be verified. Oh, okay. Thank you. Great. So, fantastic. So, this doesn't really spread out, but I think they made some statements in their paper that theoretically they could run the simulation longer and they could see it eventually relax once these long-range interactions kick in. But this is basically going more from moving away from thermalization towards integrability. And this was an experiment that came out when I was actually an undergraduate, I think. So, yeah, it was really hyped up when I started in graduate school is what I was thinking about it. Sorry. So This basically is an amazing test of integrability. What they did is they took a 1D interacting Bose gas, so you can make the contact interaction truly local, okay, and large. And you can ask, this is an integrable system, does this thermalize? It's integrable, it should not thermalize, right? So they made a Newton's cradle. So if you know this Newton's cradle, right, from classical mechanics, but they did this with cold atoms. So they made a gas of rubidium, they made a gas in the middle, and they hit it with 2 kicks. One move it to the right, to the left. So they separate the cloud, okay? The cloud separates, and then it's going to come back. And the question is, does it collide? Or does it go through each other? Okay? And what they saw was it just goes through each other and oscillates back and forth, a large number of times. It's a really remarkable demonstration of integrability. Now we come more recent. This is a demonstration of integrable dynamics on a superconducting processor. Oh, please. Yes.
Time of flight measurement, why the setup?
Absolutely, it's destructive. So you have to redo it
Then you do it like
every time. So each of these images is a huge number of measurements. But you try to prepare it exactly the same and you redo it, right? Because every measurement, you collapse the wave function, right? You get one shot, rerun.
You do it up like time period T, then 2T, 3T.
That's how you get these, exactly. Thank you, very good question. Yeah, time of flight imaging is destructive, right? Like you let it go, right? So, yeah. So now we go to the superconducting qubits, and this is realizing the XXZ model, which I imagine people around here know quite well. It's integrable. And here what they basically saw is a bunch of domain wall dynamics. I didn't want to get too much into the nitty-gritty here, but the point was that these are completely consistent with the beta-Ansatz solution. So I think this was like maybe 12 qubits, but they have enough controllability to really engineer precisely this Hamiltonian, no other terms, okay? I think that's also a very important point. Observations of many-body localization, I mentioned some earlier, though, many-body localization we talked about last time is also being debated. So we can't, these are tests of the ideas on small sizes. So here's Chris Monroe's data up to 10 ions, and they saw, if you have no disorder, it relaxes and you make the disorder large, and the magnetization does not relax. Okay? Superconducting qubits also probe many-body localization as well, and so here you're seeing the lack of relaxation, and then these are like effective parameters going basically above their expected thermal value. So this is the difference between localized and delocalized. But these are, again, small sizes, and so on and so forth. Okay, so that's kind of like the era of unitary dynamics. We built these machines, and we were always thinking about unitary dynamics, but as has already been pointed out, we need to do error correction. These need to be error corrected. At the same time, we want to learn something about them. We want to manipulate them. So we don't want to just let them run blindly. We want to do something with them. It means we need to measure them. And we need to measure them in the evolution. Okay, so I'm going to end my talk by talking about this. It's going to set us up for the next lecture where we're going to study the physics of monitored dynamics. So the idea is, if we want to learn something about it, we need to measure the system. To measure, I'm going to have to think about open quantum system dynamics because I have to couple it to my measurement device. And now, if I have these measurements as part of the error correction, these local measurements are now part of the dynamics. I can't just think about dynamics as unitary. I have to think about the measurements as being fundamentally part of my dynamics, as non-unitary aspects that's going to enrich the possible dynamics that you can have in a quantum system. So since these are part of the dynamics and they're going to be happening throughout the evolution, we're going to call these mid-circuit measurements, okay? And, oh, please.
Not true that at least error correction protocols and look at and on a system.
Yeah, that'd be coupling it to a device, and then you choose that particular channel. I mean, that's you couple to an ancilla, so. Yeah, it's non-unitary. You lose information. It's a non-unitary evolution of the wave function. So that is inherently beyond unitary dynamics. And as you'll see next lecture in detail, we have phase transitions driven by measurements in the entanglement. Whether those happen in linear observables is a big question. That'll be lecture 4. Okay? And that is, you have to add feedback to make it visible in linear observables. But if you want entanglement transitions, measurement can do it. But it's a little esoteric because it's exponentially hard to observe. But I'm going to talk a lot about that next lecture. Thank you. Any other question on that? Great. So, we all are familiar with global measurements collapsing the wave function. We're just describing time of flight, right? So I just like to show this image because these are all people really upset and dwelling on the fact that this, if you measure, you project the wave function, and what's not true, you have to renormalize the wave function, okay? So this is why it's beyond unitary, it's nonlinear on the state. The 1 over the square root of psi makes it a nonlinear operation, okay? So it's not a linear evolution anymore, which enriches it actually greatly. It's quite interesting. But let's compare a global versus local measurement. Okay, we're all familiar with global measurements collapsing, but you maybe not have thought about a local measurement so much. Let's take 3 spin halves. I'm going to prepare this in some random page state, irrelevant. I'm going to make measurements. Let's say I measure all 3 spins. So I measure all 3 spins and I get up, up, down. I project up, up, down, and I renormalize. So here's my final state. It's unentangled. What if I measured only the middle spin? If I measured only the middle spin, I project him, or whatever, project that spin to be up, and then I renormalize, right? But what you see here is I have an entangled superposition remaining. So entanglement survived my local measurement. That's an essential piece. So now, this is a theoretical point of view. Now these are very much experimentally accessible. First to come online was superconducting qubits due to mid-circuit measurements. These were released for everyday use to people using these devices. 2021. This comes back to your question actually about the atoms. So now if we think about doing this on the neutral Rydbergs, you basically have to deal with the fact that your measurement is going to fluoresce that atom and it's going to disturb the other atoms and you're going to have a lot of loss, and it's not going to be the measurement you thought you were doing. It's going to do a lot of other things. And I should say that there's a paper that preceded this that used 2 species of Rydberg atoms. And then you could use one species to do the measurement and the other to be your system. So that's why the Rydbergs really kind of came before the ions. But now what they realized, this is really a very nice paper where they shelved you can't see this very well, but they take the atom they want to measure and they shelve it to a state that's dark all to the other site, so they can measure it on that resonance. And that resonance is so far detuned from the rest of the atoms, they don't feel it. So when it emits that photon, it's just totally irrelevant to the rest of the atoms. Really clever. Yeah, please.
They identifying the error and then correct it. You don't need to identify to correct. Most of the time you look at it.
Right, for stabilizer codes.
In this case, actually, you get to identify the physical error. Advantageous in certain error correction protocol.
Absolutely.
So yeah, you can take advantage of it.
Thank you. Absolutely. You're using a lot more information, right? Than just like you can do a measurement and just an automatic kind of reset to do the correction as well. Which thank you. Yeah, very good. Totally agree. Yes.
Error. The measurement is on one species, which itself will have many atoms. Right?
So in this case, this is one. Now I have one species. So this I mentioned one experiment had several species, but this in 2023 is with one species and you shelve it. But even when you shelve it means you put it in so you have a bunch of atomic levels. When you say shelve, you put it in a level that's dark to all the other levels. It's very far detuned from the other levels. So when you manipulate that atom, the other atoms don't feel that laser because that laser detuning is just so far from those energy levels. You see what I mean? Because you're always addressing, resonant levels, right? So you put it in a level that's not resonant, and so you just and you measure that one atom and you put it back. It's pretty cool. And so, but yeah, you're right. You have to have local information. His point was that sometimes for error corrections, you don't need that local information, but now you actually can have it, so we can take advantage of it. So it's fantastic. So here's the lab of Crystal Noel and colleagues, and they basically were able to also now. This is 2025. You see, now they can do this with ions, and they had 2 different ways. They had this again shelving method, but they had this more like kind of hands-off method, which I didn't understand as well, so I'm just not going to comment on that. But the shelving method is very similar to what I just described, but for the ions. Okay? And I also want to point out that measurement also could be used as a resource. You could do measurement-based quantum computation. Instead of doing gates and measurements, you could be doing all measurements that don't commute. And measurements don't commute can produce entanglement. You can produce all sorts of quantum computation processes. Also, what's been realized, so when I was young and growing up in physics, everybody said if I wanted to prepare a topological state, I had to have a very deep circuit of order L deep. And this notion of bringing measurements into dynamics revolutionized that perspective, because you could do this in a step of one, okay? Incorporating measurements. So you can compare topological states in one shot using measurements. And they realized non-abelian topological order, they braided anions. It's really remarkable stuff they were doing. The idea is if you have a topologically ordered ground state, not just entanglement. So if you have topological order, you have non-local entanglement. And so if all you have is unitary, if all you have is unitary operations, you have to run it of order. If you have L qubits, you have to go L deep so that you can fully entangle and get that long-range entanglement everywhere. It's my understanding of topological order. Preparing topological ordered states. But this basically just completely went around that. Completely went around that because you didn't use unitarity anymore.
That leads to stay far away. You start from a product state.
Yeah.
And the number of layers you need in the layers scales with the system size.
Yes.
It gets exponentially expensive. Now you have a short circuit. It's like some like a wormhole.
Yes.
If you use non-unitary, which is like the measure.
Totally.
Or some
sort of teleportation kind of effect.
short circuit.
It's very ingenious. I mean, Rubin was obviously a driver of a lot of these ideas. Rubin Person, his work, I recommend. He really drove a lot of these ideas on realizing these states of measurement. Yes.
Because what it means that measurement can create entanglement, and entanglement is a result.
Yeah, so that's what I'm trying to tell you. It is costly, right? So this is what I've been trying to. So 2021, right? So that's kind of my point is that it's costly and there's other errors there's errors from measurement, right? That I also had mentioned earlier on, but I didn't really harp on. But the measurement has error, and then there's a time scale for the measurement, and then if you want to do feedback, that's a time scale. So the lecture 4 will talk about feedback. In great detail and like the physics we get from that and from the stuff that I'm interested in. So you'll see it really as a resource there. We'll be able to control chaos, for example, on a quantum computer. Yeah, but it is hard. The point is it's hard and you need ingenious ideas, but it's a necessity. It's a necessity, right? To really have a fully operating quantum computer, mid-circuit measurements have to be there. So it's not like we're making some artificial thing thinking about measurements. It's really it's got to be part of the physics, Okay, so I just want to end. I'm going to end here. So now the idea is, can we use the measurement outcomes to correct errors in real time? This would be feedback. Sometimes we call it feed forward. So this is going to allow for quantum error correction, quantum state preparation, and I'm going to get into the control of chaos in lecture 4. So for example, here's a recent example of the surface code from Google Quantum AI. And they were able to do distance 5 surface code. And this is a sub-extensive number of feedback operations. So this is measurement to now doing feedback, but the number of those are way less than the number of qubits they have. You can also these are 2 theory papers pointing out that with measurement and feedback, you can prepare almost any quantum state. Here's a demonstration of preparing the AKLT state with measurement and feedback, though I don't think either of these have been achieved on a device. And here's our work I'll talk about in lecture 4, where we're going to control chaos using measurement and feedback by taking these classically chaotic systems I told you about last lecture, the Bernoulli map, and embedding it onto the quantum computer. Okay. So with that, I'd just like to end. So thank you everybody for the nice questions. Hope I convinced you that ultra cold atoms are this ideal analog quantum simulator. From them, we can build out trapped ions. They offer long-range interactions and also aspects of quantum computation. Neutral Rydberg atoms offered a whole amount of flexibility thanks to the optical tweezer arrays, and it provided a new route to quantum computing. Superconducting qubits use the macroscopic effect of quantum mechanics to get and have very fast gate speeds. There are lots of possibilities for different types of qubits. Mid-circuit measurements and feedbacks are a new route to controlling the systems, and in the next 2 lectures, we're going to explore the new type of dynamics that comes when we put them into the system. Okay? So I'd like to thank you for your attention.
Thanks, Jed. People online, feel free to unmute yourself anytime during the lectures. So if you have any questions, please ask. If you're unable to use voice, you can type here preferable would be to directly ask, but I can read out the questions if there's something in the chat window. Is there any questions?
I had a question. So, am I audible?
Yeah, go ahead. Go ahead.
Am I audible? Yeah.
Yes,
So,
yes.
in the last part where you're talking about creating topological order from trivial order by doing measurements, are these measurements local? If that is the case, then doesn't it mean that topological order can be destroyed by local measurements? So, what's the catch?
So they're local measurements, but they're preparing the topological state. Maybe
But that would mean that. Okay.
you can go ahead. Sorry, I maybe didn't understand your.
Would that imply that? So if I think of the measurement as coupling to another ancilla qubit or ancilla degrees of freedom,
Okay.
then this would mean that some collection of unitaries that couple the system to some ancillas would destroy the topological order easily. So some non-local information is sort of destroyed very easily by depth one circuit. So what's the catch? That I thought that topological order should be preserved until you apply a highly non-local unitary.
So I may be misunderstanding your question because I'm not saying it's destroyed. I'm saying I'm preparing a topologically ordered state from measurement. I'm not destroying it.
But then if I think of it as a unitary circuit coupling to ancillas or ancilla qubits, then I can reverse the process and
But then you have to
create
make a measurement of your ancilla qubits, don't you?
Yeah.
So then you're always going to have to make a measurement. So you can't get around that. I mean, you want to make the whole universe unitary. I mean, you could try to do that route, but I think at the end of the day, you have to make a measurement.
I see.
You see what I mean? Like you can couple it to an ancilla, but then you have to measure the ancilla. If you don't measure the ancilla, then it's, you don't actually do it.
Okay, so this doesn't make the topological order fragile to local perturbation.
No, I think it's not. I think it's quite stable.
Okay.
Quite stable. Yes, please.
So just following up on Srijit's question, does it mean that mathematically the inverse does not exist? You can't. If it exists, then his question is completely valid. You're basically going from a product state in one.
Yeah, I think you can't. It's not you. You can't. You can't go backwards. That's true.
There is no inverse of
There's
that.
no inverse. That's right.
If it is, then his
non-unitary.
Completely valid.
It's non-unitary.
Yeah.
And how it's
That's
constructed. Yes. Yeah. Thank you.
It's not unitary, and you can have transformations which are not unitary, but inverse exist. In this case, the inverse also does not exist. So in that case, I mean, you can't really go reverse. And
Thank you.
Then I think, yeah.
Thank you.
Nice question, actually.
So was that clear? Is that clear? Sorry. To you on Zoom?
Yeah. So I hear that, but yeah. Okay, but sort of answers my question. Thanks. Yeah.
It is subtle. Yes, it is subtle.
Okay. Any questions from here or Zoom? Any further questions?
Yeah, I have one question.
Sure. Go ahead.
So Jed, you talked about this feedback things are very important for designing quantum computers, right? So to me, I mean, what I understand from designing like these quantum circuits, what the quantum simulations are done mostly on these circuits, where like you do projective measurements at each site, random or selecting like that. It's kind of unitary or random unitary circuits. So in that case, I mean, like the way I understand this feedback is like because even if you're not making measurement, it can still affect your system, right? There is some kind of feedback loop is there. Like kind of this no-click limit in quantum jump dynamics, something like that. But in these circuits, if you are making measurement strongly and projectively, I mean that feedback is not somewhere present, right? So how do you incorporate that, and how this feedback thing is important there in that case?
So I don't think I fully. So I didn't fully get your. So you're trying to distinguish dissipation and measurement. I didn't really.
Yeah, it's kind of that. So
okay, yeah. So I think the dissipation. So if you take, it's a very good question. So if you take a density matrix and you unravel, you can unravel that to a stochastic Schrodinger equation, just as you said. And a jump is like making a measurement. Right?
yeah.
But the fundamental thing here is that you do not know the outcome of that measurement. That measurement is in physically it's hidden to you, and you have to average over it to reproduce the density matrix. But if I have a measurement, I do know the outcome of the measurement. That's the fundamental difference. And then if I know the outcome of the measurement, I can make a nonlinear average over the density matrix in principle, which would access entanglement measures, which would, for example, the jump operators would not let me have. But just to make a comment, there's actually work that looked at that stochastic Schrödinger equation distributive dynamics and just said, let me imagine I did know the outcome, right? And then it just looks like a measurement. Does that answer your question?
Yeah.
Yeah. So
No, I was just thinking about this feedback, how you incorporate this feedback in circuits.
this feedback will be incorporated as an additional unitary conditional on the outcome of the measurement. It's going to be a conditional unitary operation. You can say that's what feedback really, or whatever you want to call it, feedback feed forward is. It's just a unitary that is based on what you measured. And you can imagine, the feedback I'll talk about will be rather simple, but you can imagine designing very sophisticated feedback, even like machine learning or something that, is dictating how you guess what the unitary should be. Things like this can be very sophisticated, but those timescales don't yet exist. I mean, the feedback operation has to be very fast still. So as far as I understand, these devices don't allow you to have, a bit of wait time to make a, classical calculation or something to decide what unitary to do. So the feedback I'll present will be very primitive.
Okay. Thank you.
Thank you. Thank you for the questions.
Okay. Any further questions? Anybody else on Zoom? Okay, so if not, let's thank Jed again, and we will see you all next week.
Did you get the chat? There's 3 in the chat, or?
Yeah, I think chat is fine. I think
Okay.
there's no message. It should be fine. Yeah, I think there was one message about using the mic while asking questions. Yeah, we'll try to do that. We will.
Oh yeah, we
make sure.
should. The audience.
Yeah.
Okay.
Yeah. Sorry about that. Yeah, we
Thanks
will.
for tuning in.
Yeah.